Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Lesson 21, Ptolemy's Theorem. Okay, opening exercise. Ptolemy's theorem says that for a cyclic quadrilateral ABCD, AC times BD, that'd be a diagonal, times a diagonal, equals AB times its opposite side CD plus BC times its opposite side AD. So it says with ruler and a compass, draw an example of a cyclic quadrilateral. Label its vertices A, B, C, and D, and draw the two diagonals AC and BD. All right, so I'm just going to use the ruler because the circle's already drawn for us. So if I put the ruler so that it's right on 0, the ruler, there's a location where there is a 0, and I rotate it. I'm just going to try to find integer values so it's easier. So there is a 4, distance of 4. Let me just try to get that as exact as possible. There's a distance of 4. So if I drew a segment from there to there, and I called this A. This point here, A, and this point here, B. That is a distance of 4. So AB equals 4. Okay, and I'm going to rotate and move my ruler so that B is right at 0. I'm trying to be as accurate as possible here. This is really difficult with this program. It'd be so much easier on a piece of paper. But for the video purpose, I'm doing it here. I will make this side 3. So then if I draw B, C to here, a distance of 3, then C is right here, and it is length 3. So BC equals 3. And then if I draw another point somewhere on the other side of the circle, maybe down here, it doesn't matter. And maybe I'll move that in a moment, but I'm just going to try to find a third integer value. So I'll put that as close to where I had the end of that line segment, which is right there. Move this over, and I'm actually going to move this further. I'm going to move it over here to 6. So I'll move this point right here over to here, and that will be 6, distance 6. So if I draw this red line here, CD is length 6. Okay. And then finally, connecting A to D, and we're done. With our construction anyway. I'm trying to get 0 right on A as close as possible because it will make a difference with our decimal values. Okay, right about there. And then I finally draw in a D. Okay, so it's a kite. It looks like a kite anyway. It's not quite. It's a quadrilateral ABCD. Okay, so, and how long was AD? I forgot to say. All right, that one was not an integer, obviously. It looks like a distance of 6.1234. Let's call it 6.4. So AD equals 6.4. So AB was 4, BC is 3, CD is 6, and AD is 6.4. Now I need to connect A to C. Okay, so A to C. And that looks like a distance of 6. And then I'm going to do BD. So I put B or D 0. B is right there. Draw this segment. And it looks a little shy of 7. I'll call that 6.9. So BD equals 6.9. Now I'm just going to say right now, this may not be exact because of the way I have to calculate it. As you can see, this is off a little bit. The distance might be off by 1/10 or something like that. So anyhow, I'm just going to fill this in, and it may be an approximation. It may be not exact, but it says here that AC, which is 6, times BD, which is 6.9. Okay, the product of the diagonals equals the sum of the opposite sides. So AB is 4 times the opposite side of 4, which is CD, which is 6, plus BC, which is 3, times the opposite side of that, which is AD, and 6.4. Okay, so there are our values for this. So I'm going to turn this on, and 6 times 6.9 is 41.4. So the answer over here should be close. So 24 plus, and 4 times 3 is 12, carry the 1, 18, 19.2. So 41.4, and this would be 0.2. So I'm off by 2/10 already. 9 and 4 is 13, carry the 1, and I get 43.2. Okay? But keep in mind, I'll put an approximation here. Keep in mind that I'm off by a little. If I changed, this value is a little bit more, and I change it to 6.1, then 6.1 times 6.9 is 42.09. And if that was 6.2 times 6.9, I get 42.78. So it's getting closer and closer as my decimal values are closer and closer. So in actuality, this is true. And my diagram is just off a little bit by measurement. Okay. So it says with a ruler, test whether or not that claim seems to hold true. And it does seem to hold true. It's really close. And again, I'm off just by decimal approximations. Okay, so now it says challenge, draw a cyclic quadrilateral with one side of length 0. Well, what's going to happen there is if I put a point right here and call that A, and I also call it B because the length of AB equals 0, then that's just going to shorten this side up. It would actually move this side over to here. What's that going to create? Well, it's going to create a triangle. So I'm going to put C over here, and I'll put D down here. And I'm not going to measure this time where they go, but I will measure when I draw the segments. So now I'm going to measure and draw at the same time BC. I already know AB is 0. And this is segment BC. So starting at 0, going out to C, that was 5.5. Going out to C, BC equals 5.5. AB was 0 because A and B are at the same location. I will rotate and measure over here first since I'm already at 0 on A. And that looks like 6.7. So that is AD or DA equals 6.7. So now I'm going to measure DC. So I'm trying to get as close as possible to D. Okay, I was holding my breath there. All right. Measuring DC now. The line segment D to C is right here, and that looks like it's 5.5, 5.6, 5.7, 5.8. So CD equals 5.8. All right, and I didn't measure, I did measure AD, I didn't draw AD. Okay, so what's going to happen here? Well, we have AB, we have BC, we have CD, we have AD. What do we not have? The diagonals, AC, but AC equals BC because A and B are at the same location. So AC is going to be 5.5. And then BD is the same as AD because A and B are the same thing. And the length of AD was 6.7. So there are our lengths. And how is this going to set up? Well, we take AC, which is 5.5, times BD, which is 6.7. And that is going to equal AB, which is 0, times CD, which was 5.8. Doesn't matter what CD is, that's going to be 0. And then BC is 5.5 times AD, which is 6.7. Okay, so now I'm going to calculate these. 5.5 times 6.7 is 36.85. And that's going to equal 0 plus 5.5 times 6.7. Look at that, 36.85. So that came out to be right on with my measurement. So I did better on this one than I did with this approximation. These came out to be both 36.85. So what shape is this cyclic quadrilateral? It is a triangle. And does Ptolemy's claim hold true for it? And the answer is yes. And if we think about this, it's because what did we multiply? We multiplied AC times BD. So this side times this side equals BC times AD, which is the same thing. Okay, so it does hold true for the triangle as well. Okay, page 2, exploratory challenge, a journey to Ptolemy's theorem. Okay, the diagram shows a cyclic quadrilateral A, B, C, D with diagonals AC and BD intersecting to form an acute angle W right there. Okay, AB equals A, BC equals B, CD they're calling C length, and AD is the length of lowercase d, as it says here. So it says from the last lesson, what is the area of quadrilateral ABCD in terms of lengths of its diagonals and the angle W? Remember this formula for later. So hopefully you remember this, but if not, and you have your module open and you've done this lesson, flip back a couple pages and look it up. So it's area of ABCD, the quadrilateral, equals 1/2 one diagonal times the other diagonal times the sine of that angle. So we are going to be using this formula later. So B says, explain why one of the angles, angle BCD, angle BCD, which is right here, or angle BAD, which is right here, has a measure of less than or equal to 90 degrees. Okay. The reason is opposite angles of a cyclic quadrilateral are supplementary. So if what I would say is angle A plus, I don't want to just use one letter. That's not good. Angle, let's use angle BAD. Angle BAD plus angle, and I should say the measure of, plus the measure of angle BCD equals 180 degrees. So if BAD is 90 degrees, then BCD has to be 90 degrees. That's one reason. So it has to be equal to 90 degrees, or one of them has to be less than. So then if I said the measure of BAD plus the measure of BCD equals 180, which it does, and then I give a value of angle BAD, that looks obtuse. So let's call that 100 degrees. If BAD is 100 degrees, well, then BCD has to be 80 degrees, and that is less than 90. So that's why one angle has to be less than or equal to 90 degrees. We cannot have opposite angles, both obtuse, or it would not be a cyclic quadrilateral. Okay. Part C, let's assume that angle BCD, this one right here, in our diagram is the angle with a measure of less than or equal to 90 degrees. Call it measure V degrees. What is the area of triangle BCD? So we're looking for the area of a triangle. So let me label it. This triangle right here. What is the area of triangle BCD in terms of BC and V? And then what is the area of triangle BAD, the other one, and I'll label that one in blue. Then they're talking about triangle BAD, which is right here. Okay? So we want to know what the measure of angle BAD is in terms of A, side D, and V. What is the area of the quadrilateral? Okay, so there's a lot of stuff going on here. Okay, so with what we set up here, the opposite angles being supplementary, then the measure of angle BAD in terms of V would be 180 degrees minus V. That would be this angle here. Okay, so the area of a triangle in terms of two sides and an included angle is going to be the area of triangle BCD is going to equal 1/2 one side times the other side times the sine of the included angle. Okay, so it's going to be 1/2 BC sine V. All right, and the area of triangle BAD is going to equal 1/2 A times D times the sine of 180 minus V. Okay. Or we could say 1/2 AD, A times D times the sine of just V, if they're equal. Okay, so the area of the quadrilateral ABCD is the sum of the areas of the triangle BAD and that. So that would follow that the area of ABCD would equal 1/2 B times C times the sine of V plus 1/2 AD times the sine of V. Okay. And then I could factor that and say 1/2 sine V of AD plus BC. Okay, so part D says we now have two different expressions representing the area of the same cyclic quadrilateral ABCD. We have this one up here, 1/2 AC times BD sine W, or we could have 1/2 BC sine V plus 1/2 AD sine V. So we're talking about this one, not this one. Don't simplify it and you don't get back up. Okay. Actually, it is different. 1/2 AC BD sine W, or 1/2 sine V times AD plus BC. All right. Okay, so here's what we're going to say. Equating the two expressions gives us a relationship that does admittedly use the 4 side lengths of the quadrilateral and the 2 diagonal lengths, but we also have terms that involve sine of W and sine of V. These terms are not part of Ptolemy's equation. All right, page 3 brings us to part E, and it says to trace the circle and points A, B, C, and D onto a sheet of patty paper. So this was the original circle with the cyclic quadrilateral inside of it. And if you copy that onto a sheet of patty paper and then flip the patty paper over, this is what it would look like. Patty paper is really thin, see-through paper that you can trace with. Then it says to reflect triangle ABC about the perpendicular bisector. Okay, so for starters, I'm not going to draw this in with my straight segment tool because it's just off of vertical and it will snap. So this is best I can do here. This is AC. This is the perpendicular bisector to AC right there, and showing it with that right angle. So it says we're going to reflect triangle ABC. I will show that. So triangle ABC is right here. Okay, and you see how that snaps. That's why I wasn't using my tool to draw this. See, it will not get any closer. That's the best I can do. So triangle ABC is right there. We reflect it and it will end up being, let me just draw this so it doesn't follow. So this is the triangle reflected right here. Okay, so it got reflected over. So it says, what does the reflection do with points A and C? Well, they just interchange locations. They switch. So A is going to be the same as C prime, and C is going to be the same as A prime. So A is here, that would also be C prime. So C would have flipped over to A, and A would have flipped over to C. So this would be B prime, I'm sorry, C prime. Actually, that is C, that would be A prime. A prime would end up here. Here's A, flip it over to A prime. Here's C, that flipped over to C prime. B is here, B prime is right here. Okay, so that's problem number 1. Okay, part 2 says, is it correct to draw B prime as on the circle, and explain why or why not? Okay, that's kind of a lengthy explanation, so I'll just bring it in because it'd take me forever to write it and you'll be able to read it. Reflections preserve angle measures. So the measure of angle B will be equal to the measure of angle B prime when you flip the patty paper over. Thus, angle AB prime C will be congruent to triangle or angle ABC. And also, angle ABC is supplementary to angle CDA. Let's say that again. Angle ABC is supplementary to angle CDA. Yes, because they're opposite angles in a quadrilateral that are in a circle, which are called cyclic quadrilaterals. Okay. This means, oh, and thus AB prime C is 2. So since this would now be a quadrilateral over here, then this would be supplementary to that. Okay. This means that A, B prime, C, D is a quadrilateral with one pair and hence both pairs of opposite angles supplementary. Therefore, it is cyclic. This means that B prime lies on the circle that passes through A, C, and D, and this is the original circle. Okay, so there's the lengthy reason. Okay, part 3 says to explain why quadrilateral A, B prime, C, D has the same area as quadrilateral A, B, C, D. Okay. All right, here we go. Let's see. Another lengthy response. Well, this one's not too bad, I guess. Here we go. Triangle ABC, triangle A prime, or I'm sorry, A, B prime, C, which is this green triangle right here, is congruent to triangle ABC, which is the blue one over here, by a congruence transformation, or reflection. So these triangles have the same area. It now follows that the two quadrilaterals will also have the same area. Okay, part F says the diagram shows angle having degree measures U, W, X, Y, and Z. All right, so let's just point these out. This diagram here shows degree measures of U, X, Y, Z, and W is here at the intersection of their diagonals. Find and label any other angles having degree measure U, W, X, Y, or Z and justify your answer. Okay, so I'm going to start by highlighting an angle like so. This is angle Y. All right. So it intercepts arc AD. So then I want to know what other angle intercepts arc AD, and it is angle ACD. So angle ACD is going to be congruent to angle Y. So I'll put a Y there. Okay, because they share arc AD. They intercept, they both intercept arc AD. So there's one. All right. And then if I focus on Z this time, let's see where Z goes. Z goes like this. So Z, if I get these out of the way, here's angle Z intercepting arc CD. What other angle intercepts arc CD? Well, here it is, oops. And if I put this here and bring that like that, then you see that this angle and that angle both share arc CD. So therefore, this angle is also going to be equal to Z. All right, now let's focus on X. So let me move my dash lines out of the way and let me move this down to here. Where does X go? X goes over to C. And X goes up to B. All right, I'm having this snap issue there, so just that's close enough. Here's angle BAC, which is X degrees. What other angle intercepts arc BC? Well, you put one end of your dash line at B and the other end at the same angle end that intercepts the same arc. So we have angle A, or angle BAC is X degrees. And if I put this here, that goes to the same endpoint as AB, it's DB. And then if I move this to here, then this dashed angle, angle BDC, will be congruent to angle BAC because they both intercept arc BC. So since this is X, this will be X. Okay, so we've dealt with W, we've dealt with Y, X, and Z. Now we want to focus on W. Well, vertical angles are congruent, so this will be W. And W intercepts arc CD, and so does, let's see, nothing else, but they're vertical. So that's what we want to discuss there. So the vertical angles are congruent. So if I move these out of the way, this is W and that's W. All right. Okay, now let's focus on angle U. We haven't focused on angle U yet. So this goes back here. This will go to here, and this will come up to here. So angle U intercepts arc AB. So then I want to find the other angle that intercepts arc AB, and it's right there. So angle ADB intercepts arc AB. So that means this angle is U. So we have UX, ZX, YZ, UY. Vertical angles are congruent, so they're both W. These would be W minus 180. I'm sorry, 180 minus W. Can't be negative. 180 minus W, but they don't want that. I guess we could say that. This is 180 minus W, and this is 180 minus W. Okay? So find and label any other angles having degree measures this. So I guess the 180 minus W wouldn't have an angle measure of any of those, so I will erase that. All right, so there it is. If it said in terms of W, then I would write 180 minus W. Okay? So that's that problem. Okay, page 4, part G. It says to explain why W equals U plus Z. Okay. The angle with degree measure W, which is in the middle, is here. They gave us U to be here, and Z is over here. Well, the reason W equals U plus Z is simply because of our exterior angle theorem, or remote interior angles. So if you focus on this triangle right here, that right there, W is an extension of side B to here. We didn't name that intersection. Okay, so if W is an exterior, then it's equal to the sum of the two remote interiors. So W equals U plus Z because of that. So I will bring in that in words. Okay, so the angle with degree measure W is an exterior angle to the triangle with two remote interior angles U and Z. So it follows that W equals U plus Z, as I drew in the diagram. H says identify angles of measure UX, Y, Z, and W in your diagram of the cyclic quadrilateral A, B prime, C, D from part E. Okay. Okay, part H says to identify angle measures of U, X, Y, Z, and W in your diagram of the cyclic quadrilateral A, B prime, C, D. So now we're focusing on A, B prime, C, D, this quadrilateral. Okay, so since we're focusing on that, let me draw that a little neater. Okay, that's a little better. Okay, so now we want to identify. So now, if we look, this was Y and Z. So what we would need to do is draw this segment down here and reflect that over BD. So now we need a line segment B prime or B prime D. So I would need a line segment to cut right there because I have that one there. So now it looks the same and I can now answer the question. So if you look up here, this was Y. So when I reflect over, that would be right here. Okay. Let's see. Okay, I'm going to rethink that. I'm going to take that off there. I'm going to take that off there. What I want to do is draw more diagonals here. So there's going to be another one. Let's just highlight segment AC. And then we'll go from there. So I did this because it's not snapping correctly. So there we go. So if I focus on, let me draw some segments here, make them a little thinner. If I focus on, this was Y. See how Y is up here? I do have a Y there. Well, what formed Y? This is angle Y. Okay, I'm getting that from up here. So if this is Y right here, whoops. Perhaps change back to black. This was Y right here. It is intercepting AD. Well, if you look, angle AB prime D also intercepts that same one. So this would be Y on this side. And we need to follow that guideline there. So this is going to be W over here as well. All right. So Y is AD. All right. And then what else do we know? Well, we know X is this whole thing here. So where does X go? Is there something else we can call X? So let's see. X goes from D to C, like so, and it goes up to B. So this angle right here was our X right here, okay? That intercepts arc BB prime C. Okay, so does anything else intercept BB prime C? And I can say, well, yeah, if I just move the one end that is on B prime, those, then I will find the other angle that goes to B prime, BB prime C, which is right here. So this whole thing here is worth X. Okay, so this whole thing is X. All right, so that's not real helpful. It's not an angle by itself. So let's see. This was a reflection. So X was over here. So now X is over here. X is now A, B, B prime. So if I look at that, can I find any more X's? So if I point that out to you, if this is X, like so, A, D, B prime is X, then what other line segment have those two endpoints? What other angle has those two endpoints? And if I move this over to here and move this up to here, it shares, did I do that right? Let's see, you're going the wrong place. This has to go over here and this has to come up here. No. All right, losing track here. I want to know what other angle, this was here, and this goes up like so. What other angle goes to A and B prime? Well, it's right here and right here. So I did want to go like this, and I wanted to bring this over like so. Okay, so this angle right here is X. Okay, so this is X right here. This is a little tricky. Okay, so that's X. Y goes down to here, but so does this one. So now if I focus on, maybe drawing all these lines makes it harder to see. So let's try it without and get rid of the black one here. So now if I focus on A, B, D, it intercepts arc AD. Well, so does ACD. So this would be Y. All right, so that's Y. This is X. This is Y. This is Y. I do need that diagonal though. I should not have erased that. I do need this. Okay. So with this, I have this angle here. It intercepts arc CD. So then I want to follow and see what else intercepts CD. And it would be this angle right here would be the same as this angle right here. Okay. So if this is XY, this was XY, because this angle here is now coming from this one up here. So this is X right here. Okay, and this would be Z. If you look at Z right here, CAD is Z. So this is Z here, from C to A to D, intercepting CD. So this is intercepting CD. So this is Z right here. So we have YZ, XY, and the last one is down here. This was X, I erased it. This is X. So what is this little sliver? Well, it's this. It's U reflected. So this is U. And that intercepts arc B prime C. So B prime AC also intercepts it. So this is U. So we have UZ here. We have YX here. That was from here. This is YZ. This is XY. And that's XU. Okay, that was tricky. Part I. Okay, part I says to write a formula for the area of triangle B prime A D. Okay, so let's highlight that. B prime A D is this triangle right here. All right. So we would say the area of B prime A D equals, and what are the two sides? B and D. And if we called this whole thing W, okay, W is U plus Z. And so since this is U and this is Z, and this is an exterior angle to it, then W equals U plus Z. Okay. So therefore, we have two sides in the included angle. So that is 1/2 times B times, I say B and I write D, B times D times the sine of W. Okay, so area of angle or triangle B prime AD is 1/2 BD sine W. Write a formula for the area of the triangle B prime CD. Okay, so now that's this triangle here. This triangle, B prime CD. Okay, well, we have, what's the sign of W equal? U plus S, or U plus Z, I mean. All right, so we would say the area of B prime CD equals 1/2, and we're going to use the two sides A and C. So it's A times C, and then it's going to be sine W. Because that is the supplement to it. And as we said on the prior pages, we can rewrite that as sine of W because it's 180 minus W or sine W. Alrighty, so those two equations. Let me move this over here. Okay, and part J, says, based on the results from part I, write a formula for the area of a cyclic quadrilateral ABCD in terms of A, B, C, D, and W. Okay, so we're looking at right here, based on the results from here, write the formula for the area of the cyclic quadrilateral. Well, it's the sum of those two. All right, so it's going to be area of ABCD is going to equal the area of AB prime CD. So they're going to be equal. So that's going to equal 1/2 B times D sine W, this one, plus 1/2 A times C times sine W. And finally, going back to part A, now establish Ptolemy's theorem. All right. Okay, so here's part A. I'm going to copy this and bring it over. So let's copy this. Here's part A. Copy. Go to the end of this page, and I'm going to paste it on this page. So we're focusing on this equation. So what that said was the area of ABCD equals 1/2 AC times BD times sine of W, but here we have a plus. So we're going to do a two-part proof. So the first thing we're going to say is 1/2 AC times BD times sine W from part A equals 1/2 BD sine W plus 1/2 AC sine W. The two formulas represent the same area. Then we're going to say 1/2 sine W times AC times BD equals 1/2 sine W BD plus AC. Well, what happened there was we factored. So we took a 1/2 from here and the sine W, and we just rearranged it and put those together, and we brought this down here. Okay. Over on this side, we have 1/2 BD sine W plus 1/2 AC sine W. So we factored out the 1/2, and we factored out this 1/2, and we factored out the sine W, and we factored out the sine W, and combined them here and said it is BD times plus AC, distributive property. Okay. And then we say that AC times BD, this here, equals BD times AC, because we have 1/2 sine W, 1/2 sine W canceling on both sides. Multiplicative property of equality. Okay. Multiplicative. We could also call that the additive property of equality, or subtraction property of equality. If I subtracted 1/2 sine W from both sides, they would cancel. All righty. Or we could call it substitution. AC times BD equals BC times AD plus AB times CD. Let's follow that. AC plus BD, or times BD, equals BC times AD plus AB times CD. Substitution. All righty. And that's it. I would just stick with this one right here, and that proves that AC times BD equals BD plus AC. And now let's look and see what that actually is. So AC is a diagonal times BD is a diagonal equals BD plus A times C. Okay. Okay, page 5. Lesson 21 is done. Review the lesson summary and go do your problem set. And by the way, you just finished geometry. Whew. Okay, that was a tough lesson to do. I could have done better, I suppose, but Ptolemy's theorem. Peace out. Thanks for watching.